Welcome to this video on the chemistry of the early universe. In this segment, we will explore the conditions that existed in the universe shortly after the Big Bang. The universe, as we know it today, began with the Big Bang, which occurred approximately 13.8 billion years ago. At that time, the universe was a hot, dense, and rapidly expanding state. In the first few minutes after the Big Bang, the universe was filled with a hot plasma of particles, including protons, neutrons, and electrons. As the universe continued to expand and cool, the protons and neutrons began to combine to form the first atomic nuclei. The most abundant elements formed in this process were hydrogen and helium, which still make up the majority of the universe's matter today. The early universe was also filled with radiation, which was produced by the hot plasma of particles. This radiation was in the form of high-energy photons, which interacted with the matter in the universe, causing it to become ionized. As the universe continued to expand and cool, the radiation began to lose energy and the matter in the universe began to recombine. This process, known as recombination, occurred approximately 380,000 years after the Big Bang and marked the beginning of the era of the cosmic microwave background radiation. In summary, the early universe was a hot, dense, and rapidly expanding state filled with a plasma of particles, radiation, and the first atomic nuclei. The majority of the matter in the universe was composed of hydrogen and helium, and the universe was ionized until the process of recombination occurred. In this segment, we will explore how the first stars in the universe formed. After the era of recombination, the universe entered a period known as the Dark Ages. During this time, the universe was filled with neutral hydrogen gas and there were no sources of light. However, as the universe continued to expand and cool, the gravitational attraction between the gas particles began to increase. This led to the formation of small pockets of gas that were denser than their surroundings. As these pockets of gas continued to collapse under their own gravity, they became hotter and denser. Eventually, the temperature and pressure at the center of these pockets became high enough to trigger nuclear fusion, which led to the formation of the first stars. The first stars were much larger and hotter than the stars we see today. They were also short-lived, with lifetimes of only a few million years. However, their formation marked a significant milestone in the evolution of the universe. The first stars also played a crucial role in the evolution of the universe's chemistry. Through nuclear fusion, they produced heavier elements such as carbon, oxygen, and iron. When these stars eventually died, they released these elements into the surrounding gas, enriching it with heavier elements. In summary, the first stars in the universe formed from pockets of gas that collapsed under their own gravity. Their formation marked a significant milestone in the evolution of the universe, and they played a crucial role in the evolution of the universe's chemistry by producing heavier elements through nuclear fusion. In this segment, we will explore how galaxies, including our own Milky Way, formed in the universe. After the formation of the first stars, the universe continued to evolve. Over time, the stars and gas in the universe began to clump together under the influence of gravity, forming larger structures known as galaxies. The formation of galaxies was a complex process that involved the merging of smaller structures, such as star clusters and gas clouds. As these structures merged, they formed larger and more massive galaxies. Our own Milky Way galaxy is thought to have formed through the merging of smaller galaxies over billions of years. The exact details of this process are still not fully understood, but observations of other galaxies in the universe have provided important clues. One key factor in the formation of galaxies is the presence of dark matter. Dark matter is a mysterious substance that does not interact with light or other forms of electromagnetic radiation, but its gravitational effects can be observed. It is thought to make up a significant portion of the total matter in the universe and played a crucial role in the formation of galaxies. The formation of galaxies also had a significant impact on the evolution of the universe's chemistry. As stars formed and died within galaxies, they enriched the surrounding gas with heavier elements. This enrichment allowed for the formation of more complex molecules and eventually the emergence of life. In summary, galaxies formed through the merging of small structures, such as star clusters and gas clouds, over billions of years. The presence of dark matter played a crucial role in this process, and the formation of galaxies had a significant impact on the evolution of the universe's chemistry. In this segment, we will explore how the chemistry of galaxies has evolved over time. As we discussed in the previous segment, the formation of galaxies was a complex process that involved the merging of smaller structures. This process led to the formation of galaxies with a wide range of sizes, shapes, and chemical compositions. The chemical composition of a galaxy is determined by the elements present in its stars and gas. As stars form and die within a galaxy, they release heavier elements into the surrounding gas. Over time, this enrichment leads to an increase in the overall metallicity of the galaxy. The metallicity of a galaxy is a measure of the abundance of elements heavier than hydrogen and helium. Galaxies with higher metallicity are thought to have formed later in the universe's history, as they have had more time to accumulate heavy elements. Observations of galaxies have shown that their metallicity increases with time. This trend is known as the cosmic metallicity evolution and is thought to be driven by the formation and evolution of stars within galaxies. The chemical evolution of galaxies has also had a significant impact in the emergence of life in the universe. The presence of heavy elements, such as carbon, oxygen, and nitrogen, is essential for the formation of complex molecules, including those that make up living organisms. In summary, the chemistry of galaxies has evolved over time as stars form and die, releasing heavy elements into the surrounding gas. This process has led to an increase in the overall metallicity of galaxies and has had a significant impact on the emergence of life in the universe. In this final segment, we will explore the future of the universe's chemistry. As the universe continues to evolve, the chemistry of its galaxies will continue to change. Over time, the rate of star formation is expected to decrease, leading to a decline in the overall metallicity of galaxies. Eventually, the universe will enter a state known as the heat death, where all the stars in the universe have burned out and the universe is filled with cold, dark matter. At this point, the chemistry of the universe will be dominated by the decay of subatomic particles, such as protons and neutrons. However, even in this state, the universe will still contain a small amount of hydrogen and helium, which will continue to exist for billions of years. These elements will eventually be converted into heavier elements through the process of stellar nucleosynthesis, which will occur in the final stages of the universe's evolution. In summary, the future of the universe's chemistry is tied to the evolution of its galaxies and the eventual heat death of the universe. Even in this state, the universe will still contain a small amount of hydrogen and helium, which will continue to evolve through the process of stellar nucleosynthesis.